This session should be extremely interesting, talking about quantum computing and how that relates to Viya Workbench. And so with us today, we've got our head of optimization at SAS, Yan Zhu, is going to be one of our presenters. And then from D-Wave, we've got Alex Canello, thank you, from D-Wave that's going to be a co-presenter. So real quickly before we get going, maybe if you want to just tell everyone a little bit about what you do and what you do at SAS, especially in the field of optimization, that'd be great.
Yeah, thank you, Dan. Yeah, my name is Yan Xu from SAS. At SAS, I lead the optimization team. Our team is developing all kinds of optimization softwares for external, internal customers. And recently, we have a collaboration with like D-Wave on this project. Very exciting to share the results with you.
Very good. Thank you. And Alex, if you want to introduce yourself real quick.
Sure, yeah. Hey, everyone. My name is Alex. I am from D-Wave. I am the VP of Algorithms, Performance, and Tools at D-Wave. So I'm responsible for our mathematical optimization solvers that use both classical and quantum resources. I'm responsible for our open source tools, and I'm responsible for measuring the performance of the quantum computer, hybrid algorithms, classical algorithms, pretty much anything you want to measure.
Excellent, thank you. Yeah, turn it back over to you. Take it away.
Thank you, Dan. Welcome again. Thank you for joining this session. Today, I will begin by first introduce the SAS Viya Workbench, SAS optimization, and explaining why quantum computing can be a game changer for SAS optimization. Then Alex from D-Wave will give an overview of D-Wave quantum computing, including a few exciting examples. Next, I will share the POC project. We worked with D-Wave. It is about integrating quantum computing with SAS optimization. You might have already heard a lot about the SAS Viya Workbench. If it is new to you, no worries. Let me give you a quick overview of just one slide. SAS Viya Workbench is a low-cost, low-cost cloud-enabled developer environment. It empowers SAS, Python, and R users to access data, build models, and deploy them with great speed and minimal infrastructure cost. For this proof of concept quantum computing project, we access D-Wave quantum computer through Viya Workbench. And if you're curious about to learn more about SAS Viya Workbench, you will find many great sessions at this conference. SAS view quantum computing as an accelerator, similar to CPU or GPU, that can provide rich, advanced capabilities for SAS customers. The vision of SAS quantum computing is to make quantum computing simple, fast, and intuitive. To make this all happen, right? The quantum team at SAS is working across three areas: research, products, and services. So as to research, the team is investigating the best way of integrating quantum computing, including D-Wave, into SAS the software. For products, the team is building future quantum computing products in the area AI. Those products will bring the power of quantum computing to our customer. In terms of services, the team partners directly with our customers to tackle their business challenges where quantum computing can have a real advantage. Just in this morning, you heard there is a project with a major packaged goods company was presented. That project, quantum computing project, is about solving a really hard optimization problem. And the results demonstrate basically use both SAS software and quantum computing software. We can achieve a lot of great things. And based on our experience, internal study, and also the work published by many quantum vendors, companies, including D-Wave, we believe optimization is one area that quantum computing can make a huge difference. So you might wonder, what's SAS optimization? What's optimization? So SAS optimization is a set of tools, software tools. In optimization community, we call it solvers for solving optimization problem. So a typical optimization problem has this math formula, where f is the objective function. Here is the minimization, but if you negative f, you become maximization problem. GH are constraints. X is the set of decision variables that we want to find. So when we say solving optimization problem, basically it means find the value of X that satisfies the constraint and minimize the F. That's called solving optimization. So it depends on the format of the F, G, H, X. This problem can be classified as a different type of optimization problem. For example, if F, G, H are all linear expressions, X are continuous, can only continue continuous value, then we have a linear programming. I know this programming is confusing. It's not a computer science programming. It's in optimization we call programming actually optimization. So it's linear optimization. If we further restrict some of the X can only take integer value, then we have a mixed integer linear programming. Yeah, this type of problem is very common, very important for our customers. SAS optimization can solve many type of other optimization problems, like quadratic, conic, nonlinear, black box. So I will give you two concrete examples to understand this better. This one is a picture is a weak routing problem, which is very important to like UPS, FedEx, Amazon, deliver those company. Particular instance, this one has one depot and 3 vehicle, 12 locations. The problem is basically you try to minimize the deliver cost. The constraint is basically you need to visit every location once and only once. So this problem can be formulated as a mixed integer linear programming, and also network optimization problem. Another example you might be very familiar with, this is a very simple, fully connected neural network. So neural network is the foundation of deep learning, large language model, right? Gen AI stuff. So when we talk about training a neural network or training a deep learning large language model, we're talking about solve a nonlinear programming, nonlinear optimization problem. And once we have a model, right, deep learning model or language model, we want to tune it, then we talking about this black box optimization, those hyperparameter stuff, also those optimizer like SGD parameter, epic, that's black box. So for SAS optimization, there are two ways to model and solve optimization problem. One way is through very popular model language. Proc-opt model is a SAS model language specifically developed for optimization problem. However, customer can also use Python package, SAS-opt-py, PyMO, pipe to model language. Then pass the data to model to the internal library to solve it. The other way is through model files. So user input data and the model through the model files, then SAS procedure process the model file, then call the internal libraries and get the solution. So I will reference this diagram later when I'm talking about the POC project with D-Wave. So SAS customer across a variety of industry, banking, healthcare, retail, are using SAS optimization to solve their business challenges. Just give one example here. in banking sector, a bank is using SAS optimization to determine the best timing, basically, to fill the cash in their ATMs, so that the machine will not run out of cash when customer need the cash. So their optimization model essentially helps them to reduce the number of cash out events by a factor of 10. So you can imagine that the customer satisfaction increases significantly. So that's just one example. As more and more customers use SAS optimization, so we are lucky to get harder and harder optimization problems. And the expectation on the performance keep rise. So the optimization team at SAS has been working very hard on improved performance, software performance. There's quite a lot of ways. One way is like use more efficient algorithm. Other is like to advance the code optimization, those software engineer technique. But our secret is benchmarking, strong benchmarking. We regularly run thousands of instances, test our software on those instances. So one particular benchmark performance testing task is for this solver, mixed integer linear programming solver. This one is very important. So we spend a lot of time on benchmark testing, performance testing. So particular task is have 240 problems instance. It's from popular benchmark set, and really hard problem. And we try to solve each instance in 2 hours to find the optimal solution, right? Optimal gap zero, which means optimal. And we compare our releases over last 10 years. Let me show you some results. So this bar chart, you see, different bar represent different release over the 10 years. So the left one is SAS 9.3. We only solved 68 instances at that time. It's really hard instance for us at that time. So we improve. Now we can solve 200 instances, which is more than 80 instances. If we have a faster machine, we can run, we can solve even more for each instance for 2 hours. So that's very good news. So we can solve more instances now, but how fast can we solve each instance into optimality currently or previously? The blue bar, this bar, the high is the worst. You can see. It used to be, we spend over 5,200 seconds. It's 1.5 hours on average to solve each instance to optimality. So basically maybe solve one instance, it takes 1.5 hours to prove this optimal. Take a very long time, and only solve 68. You notice. And we improve, see? Like a more law, improve. Now only take 346 seconds. It's less than 6 minutes, so from hour to minutes. And our customer really happy, right, with this result. It's about 15 times sample 4. However, if you have sharp eyes, you might notice the pace of improvement slowed down during past 2 years. It's not because my team is become lazy or we're not working hard. This is a trend observed by the whole industry, optimization industry, slow down. Every technology has its limit. So we are thinking next step, how to get out of this. Good news is quantum computing had, if you notice the news, had many breakthroughs during past year or 1, 2. And we believe quantum computing is a new computing paradigm, essentially new. It will happen eventually. And some vendors actually pretty advanced. Yeah, we think we can use the quantum computing to further improve SAS optimization, maybe by another 15x fast. We hope so. So that's why I work with D-Wave Let me ask we invited Alex to talk about quantum computing now.
Sure, thanks. Awesome. All right. Yeah, all right, quantum computing part. So, I probably should start off by giving a very brief overview of what D-Wave is. Not everyone here might be familiar with it. Main takeaway, D-Wave's a 25-year-old quantum computing company. We are full stack. A lot of folks don't really realize, think about this, think about quantum computing companies as being a bunch of scientists in the back of a lab. We have those too, they're really good. But we're also full stack. We're available in the cloud, we're high uptime, I'm gonna talk about that in a moment, and we're actually helping customers solve problems. And the other thing, I guess that brings me to the last thing you gotta know about D-Wave, is we're actually being used in production right now by a set of different customers. So we are doing optimizations for a Patterson Food Group, which is like a grocery company. We're shipping containers to the Port of LA. We are doing a body shop scheduling problem where you need to decide what order of cars to work on an assembly line for Ford AutoSun. We're doing a bunch of different stuff in production right now. So there's a lot of stuff on that slide, but yeah, you can read. As Jan mentioned, there's a lot of quantum computing news in the space. There's a lot of stuff happening. And so I also want to take a moment to talk a little bit about how D-Wave thinks about measuring quantum computing companies, how we think about being a useful quantum computing company, and also ultimately what has allowed us to get into that production space. So the framework that D-Wave likes, and you all should like too, is 3 different criteria for being a realized quantum computing platform. The first one is you need a quantum computer, you need the technology, and that quantum computer needs to do something that nothing else can do. So for instance, and D-Wave has this, for instance, a few months ago, we published our Beyond Classical result. This was an example of an application that took us 20 minutes and would take the Frontier supercomputer, one of the best supercomputers in the world, over 1 million years to do the same problem. So no project that I know has a 1 million year budget or timeline. So I'm going to pretty safely say that that's beyond classical. I think we're going to be taking questions in a bit, but yeah, good. Yeah. So the second thing, though, that you need to make your quantum computer useful to different customers is you need to have high availability. So it's not just enough to have a quantum computer. You need it to be accessible to folks like y'all. Again, check mark for D-Wave. We have 99.9% uptime of our quantum computer available via our cloud platform. So you don't need to, it doesn't go dark for weeks at a time. You don't need to wait weeks to get access to it. Y'all could sign up for Leap and get access to a quantum computer, no problem, and it'll be there waiting for you. And then finally, you need commercial success, which is to say you need to be useful to customers and they need to pay you money for the privilege of using your stuff. And as I alluded to, we have several different successful customer applications that are in production right now. People are using us in their line of business today, which I think is pretty rad. Okay, so enough about D-Wave. Let's talk about one of our products, the product that actually is most relevant to this talk, which is our optimization hybrid solver. So I mentioned earlier that D-Wave is a full-stack quantum computing company. And when I do say full stack, I mean full stack. We have several different layers of abstraction. Most folks do not want to play with the quantum computer directly. They might want to kick the tires on it. It's pretty cool. It's very fun. But it is very much, for those of you who are like software folks in the room, it's like writing a machine code. It's very low level. So we want something that's higher level. And for folks like y'all, our higher level abstraction is our optimization solver, which is exactly the same sort of flavor as solver that Jan was mentioning before. Our optimization solver, rather than get sort of into the technical details, if anyone wants the technical details, love to chat with you in between meetings, come find me. But I do want to give you like a high level overview of like what is the philosophy, what is the thing that we are trying to build so that you can have something of an intuition for like how it works and what it might be useful for. So to that end, our hybrid solver is hybrid on 2 levels. The first thing is that it uses both quantum and classical resources. But the second thing is that we are bringing together 4 different distinct streams of optimization into the same product to try to solve practical problems for you all. So the first one, and the one that's in some sense most important, or at least the most different, is quantum optimization. We have a quantum computer. We get unusual access to this. Nobody else has access to quantum optimization. That is sort of our special sauce. So that is both the quantum computer itself in our product, but also has informed a lot of our algorithm design. So Our quantum computer is natively a non-convex optimizer, for anyone who knows what that sort of thing means. That has informed the development of our product. We do not have restrictions on, say, convexity of your problem, which is something that can be a big problem when you're modeling for these sorts of solvers. The second main area that we are drawing from then is constraint programming, combinatorial variables. And to that end, the basic idea here is that normally in these optimization solvers, like the one that Jan mentioned earlier, you tend to think about variables as like an integer or a continuous value or binary. I'm going to determine how many of X stock to buy. I'm going to decide where in XY coordinate space to place my thing, those sorts of things. Very usual, very common, very usual. We do that too, spoiler alert. But the insight of this combinatorial thing is, what if we also allowed variables to be sort of more abstract objects? So for instance, rather than modeling your traveling salesperson problem using a set of n-squared binary variables, what if you could just say that the order of airports that I'm going to visit is my variable? It's just a combinatorial list of airports in the order that I want to visit. It's a little bit of a mind bender for those who are coming from the mixed integer programming space, but it's extremely powerful and has been very useful to solving a lot of problems. The third space, rather, is this mixed integer linear programming space. Jan talked about it a little bit, and I think a lot of folks are familiar with it. I won't belabor it, but we are also doing that. So we do support continuous variables, binary variables, integer variables. You can give us linear constraints. We're not unaware of simplex or interior point methods. You know, we know how to do this stuff too. And a lot of problems are formulated in this way, at least at the beginning, so we support it. And then finally, the last stream that's coming into our optimization solver is this tensor programming space. And I do think this makes D-Wave unique in this space. I don't know of anyone else who does this. Would love to learn otherwise, if anyone can tell me. But the basic insight here is the same one that TensorFlow and later PyTorch and some of these other folks had on the machine learning side, which is if you think about your problem in terms of array or matrix operations, it's actually often easier to think about it that way than to think about individual values. So we don't really talk about like integer multiplication. We talk about array multiplication in the context of our solver. And again, it's a bit of a mind bender if you're not used to thinking about things in this way, but it's extremely powerful when trying to solve problems. All right, philosophy. Okay, so let's make this hopefully a bit more concrete by running through two different examples and sort of showing how we perform on those and motivating them a little bit from why these different schools have fed into them. So the first problem I want to talk about is the satellite placement problem. So imagine, if you will, that you have a geosynchronous orbit, ARC, that you want to place a set of satellites on. Each of these satellites has a location or maybe locations on the surface of the Earth that they need to reach. That defines sort of where within the arc they are allowed to be. These satellites also interfere with each other. So certain satellites are maybe transmitting on the same bandwidth or bandwidths. So when they're really close, there's a lot of interference. When they're really far, they don't interfere, that sort of thing. So the problem is to determine what is the optimal placement on that arc to place these satellites to meet the requirements that they can see the parts of Earth that they need to see while minimizing that interference. Yeah? So you can actually express this using this equation down here. And one thing that I want to, which actually, if you look at it just sort of briefly, kind of looks like one of those linear equations that Jan mentioned earlier. But I want to draw your attention to this d sub x sub I. That's an indexing operation. That's a matrix operation. That's not linear at all. And in our solver, you can just express your problem in this way. You do not need to do big convolutions on some weird matrix tracking a bunch of stuff. You don't need to use binary variables to assign indices of things. You can just operate on it directly. And what this gives you is not only an easier way to express the problem, but a hell of a lot of performance. So in this case, we are comparing our solver to our own CQM solver, which is our own mixed integer quadratic programming solver. We're also comparing it to all the solvers that could run this problem in Pyomo. We can't actually compare this to like Highs or Gurobi or Cplex because the number, it's so nonlinear that it's extremely hard to express in those solvers. You can use a quadratic programming solver, but not a linear programming solver in order to solve this. And basically, bottom and to the right is good. Our NL solver crushes this problem. We are able to get to a much larger number of satellites, and we are able to get optimal or very close to optimal for these sizes. And we could have kept going, but all the other solvers really started falling off, and it was becoming too expensive to run them on our service. So, this is an extremely useful thing. Okay, the second problem then that I want to talk about before handing it back is the flow shop scheduling problem. So for those of you who are in operations research, this is a job shop scheduling problem. For those of you who aren't, I'm going to motivate it. Imagine, if you will, that you are a port. And you have maybe a small one, big port. We want to solve big, expensive problems. You are a port, and you have ships coming in. For each container on the ship, you have a sequence of operations that you need to do. You need to lift the container off the ship. You need to open up the container. You need to unload the cargo. You need to load the cargo onto another container, and then you need to put that other container on a truck. Yeah? Those are the sets you need to do. And for each container, you need to go through the same set of operations in the same order, although they might have different lengths of time. So the problem is, what order should you do the containers that minimizes the total time that this entire operation will take? So job shop scheduling problem for those of you who know this sort of thing, very classic business problem for those who don't. And the thing that's really neat about this problem, at least from my perspective, is that actually the optimal solution to this problem will always is uniquely defined by the order of those operations. So it always makes sense, basically, that if you're going to do this container, you should do the lift, and then the open, and then the unload, et cetera. And then if you're the second container, you should do them in the same order each time. You notice there's no intermixing, and you get this very nice cascade. I think it's quite pretty. I really like it. It's cool. So what this actually means is that if you want to know the time that you're going to be doing any particular step on any particular container, it is determined by the previous step. So basically, you can't unload a container before you've taken it off the ship, so it's either going to happen immediately after that, or the person who's unloading, you need to wait for that person who's unloading to come over. So it's going to basically be the max of the end of this operation, or the end of this operation, or the end of this operation. So that gives you this max function, which again, very nonlinear. Can't do that with a mixed integer linear programming solver. And so, once again, not only is this easier to express using that sort of max, this nonlinear equation, it also gives you much better performance. So in this case, we were able to compare to a mixed integer programming solver, in this case HIES, as well as some from OR tools, and again, our own CQM solver, as well as our nonlinear solver. And again, we get much better results. This is a log plot, so don't be confused. This is a very nice result from the perspective. Maybe I should make it not log, so it really blows up, and that looks very cool. So yeah. With that, I am going to pass it back. Thanks, everyone.
Thank you, Alex. Yeah, first, to best understand the quantum computing and also the best way to integrate the quantum computing with SAS optimization, especially, we did a proof of concept project with our friends at D-Wave. This project focused on flow shop scheduling problem, which has been introduced by Alex. And we divided this project into 3 phases. So during phase 1, we model and solve the problem in SAS Proc opt model, which try to lay a foundation for the next 2 phases. Second phase, we made a necessary software change inside our solver to add D-Wave quantum computing. Last phase, we did a bunch of experiments and gather results and derive insights and learning from the results. So in the rest of the presentation, I'll walk you through the 3 phases. Now let's talk about phase 1. Over the next 3 slides, I will show you how to model this flow shop scheduling problem in OptModel, using OptModel. I will keep it at a very high level to save time. But if you are interested in this technology, please visit the Quantum booth and dive deeper. Okay. For this code block, you see we have the jobs, machines, D. Jobs is a set of jobs like maybe a set of containers. And machines is like a set of stations or the task, like pick the container, open the container. Each task requires time, right? And also unload, load, deliver. D is the time, the task times, processing times of each jobs and each machines. So it's a 2-dimension metrics. So we store the time. And we read the data from input data file. This basically is declare parameters and input data. The second code block is about declare variables and objectives. For example, x, y, w are variables, but x is the variable we really want, is the start time of job j on machine I, essentially like a container j on this task I. So we don't have an overlap, so it's kind of have to decide the time, right? And the objective is to minimize the max span. Max span is the time required to complete complete all the jobs, like a container, all the containers. So we want to minimize the time so we can save cost. The last code block is about declare the constraints and then call the solver. Constraints like the precedence constraint, like each job, there's no overlap. This is no overlap constraint. So this is one way to call the SAS, our classic solver, like called mixed integer linear program solver, and then give us, here just give a maximum time 15 seconds. So these three blocks essentially define a model flow shop scheduling problem. We can then test it, how good this model it is. This is unscheduled data. It's, you can imagine basically this can be a container, each container, right? And this color is different operations, the processing time. This is unscheduled, start from 0. X is time. Yeah, that's the, if we imagine if we have unlimited resource or stations or tasks, basically every container can start from 0, right? And finish, basically finish, this job dominates the mix span. That's unlimited, but unfortunately in real life we have, for this we have only one station or one machine. This picture shows the schedule found by the SAS classical MIP solver. It starts from the container 10. And on this, pick up this container, this machine pick up. Then once this is finished, we start the container 5, pick up 5, the blue. So it's blue, the sequence always change, same, like blue, red, brown, this purple. So all the job is same. Then once this is finished, we start another pick. Then we have to wait for a second this station or tools machine available, then start. So this is schedule find by SAS solver. Just remember 0. This container 0 is the last one to process. And the mix span, the total time required is 7,312. Just imagine if we unlimited resources, it's about 3,000 seconds we finish it. So this is the optimal schedule because optimality gap is 0. That's great, right? Okay, let's do the phase 2, which is about incorporate D-Wave quantum computing into SAS optimization. So this is the same high-level architecture of SAS optimization. Same. To make this change at the quantum computing, the first step is add an option for user, quantum user. Second step is we develop a quantum agent inside our internal libraries. So this agent essentially called D-Wave APIs, right? Pass the model and the data to D-Wave solver, then get the solution back. So that's the change we made. Quite straightforward, and it can be powerful. From user point of view, oh, really? Oh, that's 36 right now. Okay, I have to speed up. Oh, sorry. That's surprising. Okay. User point of view, see here is solve this MIP. Solve with quantum. So we made SAS, the goal is to make the quantum computer simple, easy, and intuitive. We at least make it simple, easy, very fast. Very fast, I'm not sure. Let's see how fast. So this same problem, we call the D solver. This is schedule proposed by D-Wave. The mix span is 78222, which is worse than SAS solver. You just remember the job 0 now become first one. So you might wonder, why bother with quantum computing, right? Why bother? However, this is just one instance. Stay tuned. So we did a more thorough experiment. This time we actually use 3 instances. This one we'll talk about the 12 jobs, 5 machine. This 20 jobs, the 20 container, 10 operation become harder and harder, right? And we tested on 3 approaches: MIP solver, optimodel, through model, quantum also through our SAS optimodel, and hybrid. Essentially, this one uses the quantum solution from D-Wave and pass to our solver and warm start, see how good it can be. We did a lot of rounds and collected quite many exciting results, actually. I'll show you now. This bar chart shows this simple instance, 12 job on the 5 machines. The bar lower, the better, which is make span, right? Total time to finish all the job. So classic, this one is our solver. It's better than quantum, we know. This one we can prove optimal, essentially. The hybrid also prove optimal. But if we use this instance, harder one, you might notice the orange one, which quantum is better than ours. And the hybrid one, the great news is if we take the quantum computing the solution, we can improve it even better. It's just a few percentage, but it might save millions of dollars for larger organization. This harder one, again, quantum is better. This time we even use the quantum solution. We cannot improve it in 15 seconds. That's because the problem is harder and the time is too limited to allow the classic solver to be effective. Oh, so what we learned from this POC project? Quantum, not surprised, quantum is very fast. In our experiment, it's usually take a few seconds to get good solutions. That's really quantum computing shines. And another benefit is quantum give a variety of solutions. And we can derive insight from the many solutions, which are not obvious to limited number of solutions. Classical, when the problem is not like extremely hard or the complexity is reasonable, or we need a solution with optimality guarantee, then we can rely on classical solver. Also, classical is very effective in detect invisibility. This actually happens a lot in practice because of the modeling error or conflict constraints. So classical can detect it for you. It's another advantage. So hybrid, if we use quantum to generate a initial solution and pass to classical solver to warm start and improve it, verify it, what we get? We get a good solution, high quality solution, very fast. And those solutions, we can have confidence how good they are. Essentially, we have optimality gap, how close to optimal solution. If we're happy with 3% to optimal, then we can stop, right? We don't need to run hours. Also, we can detect infeasibility when the problem is infeasible, so it saves us time. We don't need to search forever. Classic can tell you this is infeasible, this constraint can't do that constraint. So is that every optimization user really want? Essentially, you get all the benefits of these 2 approaches and without their weakness. We did 2 more examples during the POC. I won't have time to talk about them here, but come to our booth, and we are happy to share details and give you a demo. These 2 QR codes, please take a picture. You can get the link to web page, AI web page, SAS quantum AI package, and also D-Wave representative email. feel free, take a picture. I think this is the last slides. We would love to answer questions.
Perfect. Yeah. Thank you. Before we get to questions, a quick round of applause for Jan and Alex. Thank you so much. So, if you have a question, just raise your hand. I'll bring the microphone over to you. I know there were some questions earlier. Yes, sir.
Thank you again for the presentation. I just would like to ask the question about what we hear this morning from the Procter & Gamble company about using quantum. This was part of the D-Wave solution or what?
Yeah. I believe that was with D-Wave, the one.
Can you elaborate quickly what was the main idea there? I mean, in this project.
Sorry, ask again.
Can you elaborate what is the main optimization in that project?
I believe that was this one.
That's different.
Oh, sorry. Go ahead. Yeah.
That's with a packaged goods company, which is assignment problem. Essentially, assign this thing to another thing. Particularly, that problem is assign one ingredient to a container or something, tanker, to mix the ingredients. So that's an assignment problem.
And this was with D-Wave?
D-Wave.
Just quickly, since there's no like a quantum advantage directly with the optimization.
There's not a
quantum advantage, but maybe just do you see like the big thing here because of the space, the large space that you can handle? Like since you have 5,000 spins, so the space is so huge that cannot be handled with a classical computer. Otherwise, what the quantum elements that help you in the optimization?
I see. I mean, so just to be pedantic for a moment, like there isn't like a theoretical, like provable complexity advantage for optimization problems. There's some nuance to all of this, but that's sort of the overall message. That said, I mean, I can give you a pile. I mean, we have them on our website, like a pile of optimization problems. You can run them on our system and challenge you to find a classical system that outperforms us. I mean, that's different than that sort of supremacy regime that I was describing before, which tend to be a little bit more rarefied problems. But you know, there's a scale between those two things. And so, yeah, I mean, ultimately, the advantage for optimization from our side comes from the size of problem, the discreteness. Discrete problems tend to be quite hard classically, and the sort of native non-convexity of the problem. So like our solver doesn't have any notion of convexity, whereas most of the classical solvers are trying to find some sort of gradient to follow, and we just don't have that. So like, yeah, it provides for a lot of problems, it can provide an advantage. Yeah.
Thank you, gentlemen. I think that's about all the time. Unless somebody has a quick question, kind of hard to have a quick question about quantum, but we'll try. Just one last question, and then we'll have to wrap up. Yeah.
I promise. Firstly, thank you for your time. My question to you is, how long do you think until quantum computer is implemented into society? Just a quick question, just a quick answer.
Hold on.
I mean, you know, we're running in production right now, so I would argue we're there already. I mean, I think maybe you're asking, like, when is it as ubiquitous as I don't know, GPUs? I don't know, soon. If I could predict that, I would be very rich. But like, you know, ultimately, we're already starting to see the case where people are using our hybrid solvers, which use the quantum computer, in production like right now. So you know, if you buy groceries from Patterson Food Group grocery stores, you are interacting in some sense with a quantum computer. And so like there is. You know, so there's a curve here, of course, and we're all waiting for the day that it, you know, heads off. But yeah, I think we're very much on that curve right now. Yeah.
Perfect. Thank you so much. One last round of applause for our presenters. Thank you so much.